Good afternoon, everyone. Welcome to the talk. My name is C, and with my colleague Hao here, we are coming from Uber. Today, we are going to give a talk about Kafka replication at scale in Uber. First, let's take a look at our agenda. First, we will give a brief introduction of Kafka adoption at Uber, and especially how we handle Kafka replication under this adoption and this scale. And we will talk about what kind of challenges we have regarding replication for this streaming data. And then we will start our deep dive into the replication system we have called uReplicator. We will talk about how we manage large number of replication tasks, as well as how we handle auto-scaling, rebalancing within the system. After that, we will talk about some work that we have done in the observability world that help us manage the cluster easier. At the end, we will talk about our plan in the future on several items that to improve the system. First, let's take a look at the Kafka adoption at Uber. I think many of you may have used Uber app or Uber Eats. So maybe some of you even is a Uber driver. So from your app, there will be many messages sent to our front end and then sent to Kafka. These are one of the important sources of our Kafka messages. And we have other internal data pipelines built in order to support all kinds of data engineering processing and can emit many messages into Kafka as well. Another important sources of Kafka are from the storage system. We have different kinds of storage system built to support different kinds of business use cases, from MySQL to NoSQL and document store. So all of these are the important source for Kafka. And the messages will be consumed by the downstream in two main categories. One is in real time, one is in offline. So in the real-time consumer is a very critical pillar in Uber's consumer world. One of the main cases is called the PubSub use case. We build our own internal implementation of service called consumer proxy, which is a reverse proxy that consumes from the Kafka and publish the message to the consumer service from gRPC. Other than the PubSub, we also empower streaming analytics and streaming processing by leveraging Apache Pinot and Apache Flink. So this concludes the real-time part of our consumer world. In terms of the offline world, we have Hadoop and Hudi that form the data lake foundation that empowers the data science and analytics part of the story. Regarding the scale, currently we are publishing around 17 trillion messages a day across around 38 Kafka clusters. This is generating around 10 petabytes of messages per day. And the messages are dispatched to more than 1,000 consumer services. Regarding the produced latency, currently we can do 10 milliseconds and at P90. So with this current scale, we also support Kafka messages replication across clusters and across regions. We have built a system called uReplicator many years ago. This is built on top of MirrorMaker 1. It can not only solve the challenges that the MirrorMaker 1 was facing at that time, we also build other innovation inside the system, which I will go through later. So to give a broad view, currently for uReplicator, we have around 12 clusters in order to fulfill different kinds of replication semantics, like lossless versus lossy. In each region, we have around 4,000 instances doing the replication across different Kafka clusters and across region. In one of the largest clusters, we have currently doing the real-time aggregation of Kafka topics in all the regions. We can support up to 7,000 topics today, and they are replicated by more than 1,800 workers in each region. Running such a large scale of the cluster brings us some challenges to solve. There are 3 categories. The first one is scalability. So the number of topics is growing every day. And we also have a growing demand of replication to do the aggregation for some consumers. They want active mode. So how to scale and manage this growing number of topics and scale impose a great challenge for us. And moreover, once we want to run such a large scale, we will definitely need a large number of resources. Then cost efficiency is another topic that we want to solve. How do we optimize the resource usage? How do we achieve cost efficient and have performance gain and efficiency gain is the problem that we want to solve. And we also want to reduce the replication latency for some extremely critical business use cases. After we have worked to tackle the scalability and efficiency, we also don't want to sacrifice our reliability. So how to effectively monitor and set up concrete and accurate alerts for the system, and also to achieve a best effort disaster recovery for such a system is also another challenge we want to solve. Before we talk about how we do this, let's start with a deep dive into the current architecture. I will hand over to my colleague Hao to start the deep dive.
Hi, everyone. Let's deep dive a little bit in our uReplicator architecture. That is our Kafka replication service built at Uber. The uReplicator consists of 3 major components: a manager, worker, and a controller. So the uReplicator manager is a federated layer to manage the controller and worker clusters and manage the topic assignments, and also act as a REST layer to process a request, like create the topic replication and delete the topic replication, create and delete the routes, and also act as a monitor role, like periodically to monitor the instance usage and report this usage by sending the matrix to our compute platform. Our compute platform will use this data to scale, to do the horizontal scale up and down based on this source of the data to better efficient usage of our compute instance. And all of these 3 measures coordinate by using the Apache Helix, which is the open source cluster management framework, which is based on the Zookeeper. Okay. After we know how it looks like on the architecture point of view, and next we will discuss how do we manage all of the replication tasks at Uber. First, we have to define the single unit of the replication task is. So the one replication task is a single topic partition replication job. And how do we organize all of these topic replication tasks? First, we divide all of them tasks into a different pipeline, which is identified by the source and destination clusters, Kafka clusters combinations. And after we divide into the multiple pipelines, in each pipeline, it consists of multiple routes, which is a response for the assigned topics replication works. And we can think about it as this routes is a shards within the pipeline. And each route will manage the actual set of the worker instance to do the actual like the topic replication jobs. And let's take the one of example of the what is the how do we assign replication tasks. Let's take the example of the topic A. We want to replicate the message from cluster 1 to cluster 2. The first, we should locate the pipeline. The pipeline would be the cluster 1 to cluster 2 pipeline. And then we will assign the topic A into one of the routes within this pipeline. Let's assume that will be the route 0. So the route name will be the cluster 1, cluster 2, 0. And within this route, we will assign the topic A partitions across all of the workers within the routes. It will like the, if we like the, go back to the architecture, so the controller, the uReplicator controller will control the routes and also control the topic partitions across all of the topic partitions assignments across all of the uReplicator workers. And the uReplicator worker actually is actually like the worker, the instance to consume the message from the cluster 1 and produce a message to the cluster 2. So that is how the replication task assignments works from end to end. And the next is about how do we manage all of these replication tasks. We manage all of them based on the federated cluster. There are two major clusters. First is a manager worker clusters. That is a response for like the how to assign, how many routes we want to assign in each pipeline, and how many worker instance we want to allocate in each route. And the other cluster is a controller worker cluster. That is a response for assigning the topic partitions replication job into the worker instance, and also like the works for like rebalancing the topic partition replication job across the workers from like the worker 1 to worker 2. And all of these clusters is leverage the Apache Helix to do the management, like the how to allocate the resources, allocate the task, rebalance, and the fault tolerance. And beside of the organization, task organization and management, we have some innovation built on the top of this architecture. So the main motivation of this innovation is we want to like the best effort to make the better use of our compute resources. So the main idea is like we want to balance all of the load of the replication task across the rows. The first, we will do the shuffling, like we shuffle some topic replication jobs from large routes to the smaller routes. And the second is a task merge. We merge the small routes within the single large routes. In these two ways, under these two ways, we will have try our best effort to balance all of the loads across the routes. Next, I will hand over to Si to discuss a little bit more about the autoscaler of the uReplicator. Thanks.
Thanks, Hao. So after we have go over the structure of how we manage the replication task in a federated way, the next topic we can discuss is how we scale the cluster to support such a federated organization. Because currently in our largest cluster, we have more than 100 routes. So the component functioning here is called the autoscaler. It has two main functionality. The first one is to scale the worker cluster and the controller clusters. So basically, in each of the controller within the route, it will start to collect the topic workload, such as the bytes in and message in per second information from another service called topic workload service that we have built. After it collects this information, it will calculate how many workers that this route needs in order to support this larger scale of the replication. Besides this, it will also monitor the replication progress of each topic partition within the route. If we identify there is a topic partition that with significant replication lag, either because the worker is overloaded or the topic partition has a spiky traffic, it will also take this into account into the auto-scaling. It will add this as a factor to ask for more workers. So by combining these two factors of workload-based and also the lag-based factors, it computes a final number of worker scale and send this to the metric system. Our compute platform that everything is built on top of will consume the metrics from the metric platform and then use this to auto-scale the clusters. After the number of workers or number of controllers are in place, then our manager will try to allocate the required controllers or workers into the system. So after everything is in place and we have enough resources, then within each route, we need to do balancing of the workload across all the workers. So the second important component here is the auto-rebalancer. It has multiple functionality. The first one is, of course, to make sure we have an evenly distributed workload across all the workers. And the second functionality is also very important, is to auto-mitigate or auto-healing some like failure scenario or some suboptimal scenario. These scenarios include, for example, if we have controllers or worker that goes offline because either of a deployment, a service crash, or a compute shuffling, then the rebalancer will take effect and try to replace these offline instances. The second functionality is that you remember earlier we talked about the controller will monitor the replication lag of each topic partition. So once it identifies this replication lag, it will try to use the idle workers that is assigned and move the lagging topic partitions to these idle workers in order to speed up the replication. So with these two important components functioning, we are able to scale the cluster according to the growing number of topics. But that's not enough. We also build some work in terms of observability to help us manage and scale the cluster easier. The first one is the metrics to monitor replication lag. So normally when people measure replication lag, they will usually do this by using the high watermark offset to subtract the committed offset so that you can get the number of messages that is still lagging. But to our consumers, this is not straightforward enough to know like how many messages do I need to replicate. So in order to provide a better experience for our users, we built a new matrix called time-based replication lag matrix. So this is done by our workers. Basically, each worker, because they have been assigned several topic partitions to replicate, and they are continuously committing the offset of each partition. So when they commit the offset, they will record the timestamp when they do the commit. And they will also use the timestamp that for the messages at the highest watermark. By using these two timestamps, we can calculate the difference. And this difference is the time that for the replication lag. So as you can see from these metrics, we have a result for the topic called data reliability test result. And for each of the partition, we have the replication lag matrix emitted. The largest one you can see here is like more than 40-something seconds. So with this matrix, it will be very easier for us to set up alerts and also set up monitoring to know if there's anything wrong with the system. Then the next question may come on, if now you have a lag, how do you troubleshoot? This is the second thing we have built. We have built a tooling to quickly identify the worker to topic partition mapping. By using this, we can firstly identify what's the topic partition that have a pause in the replication progress, or it has a slow replication. And then this tooling will give us a clear representation of which workers is currently assigned these topic partitions. So as you can see from this output, we have 3 partitions that are stuck, topic A, topic B, and topic C. And each topic has 1 partition that is stuck. And the ideal worker here means the worker that is currently assigned. So with this information, we are able to troubleshoot the problem by leveraging any matrix that is emitted from this worker, or we can log into the worker to actually troubleshoot what happened. In another case that we want to mitigate things faster, we can just restart the problematic worker. And our rebalancer that we just discussed earlier will quickly kick in and move the topic partition away to another available workers. On top of that, we also build a management API that we can use it to query the actual topic partition assignment within each route. For example, for a topic with 8 partitions, the current route is from DC1 to another DC1 to another Act1 cluster at the route 4. It has an external view of all the ideal assignment. And then on the right side is the ideal case. The left one is the actual assignment, but the right one is the ideal state of the assignments. But by combining these 2 information, we can quickly know whether the assignment is actually executed as expected or planned, and whether the load is also actually balanced already in each of the workers. In terms of future, we have also planned several items to improve our system better. The first one will be an isolation for different tiers of the topics. So within Uber, we have another work stream that is ongoing to identify the tier of each topic. But currently, for our replication story, we don't provide a good isolation for different tiers of topics. And this already brought us some kind of trouble to provide a customized SLA or maybe a much stricter SLA for some topics. So we have the idea to build a tier-based replication clusters for these topics. Another item is to explore on the KEEP 712 that is proposed by our friends from Pinterest. And we want to explore the shallow copy idea. This will help us have gain in terms of efficiency and performance. Last but not least, as you may still remember, we are relying on another service called topic workload service to provide the workload of each topic to the system in order to do auto-scaling and load balancing. However, this has some defect in the design. It made the system not able to be failure open. So in order to solve this, we want every worker to be topic workload self-aware so that it can report the topic workload back to the controller. And controller will leverage all this information to do the auto-scaling logic that we just mentioned. I think this concludes our presentation today. Any question?